AP Calculus students, how you doing today? We are working on section 1.4a. This is continuity and one-sided limits. At first, when we're talking about this, I'll actually write out the word continuity, but that gets to be a bit aggravating after, because we write continuity and the word continuous so often. And so you'll see all through calculus, I'll use a C with a circle on it so that I don't have to keep writing continuity and continuous. This also means then if there's a discontinuity or something is discontinuous, I will use a DC with a circle around it. And I have some other abbreviations that you'll get used to so that we can focus on getting our job done. So we already know quite a bit about continuity and one-sided limits because we talked about limits in section 1.2 and 1.3, and we said, we have to talk about the limits separately from the value of the function at that x we're approaching, but very often the limit does equal the value of the function because we have nice, well-behaved, smooth functions that we call continuous because we can draw them continuously. But we need to be a bit more detailed about that, about what continuous really means. We are going to be looking at the continuity test, incredibly important. The continuity test is on the AP exam. It's not that they ask you what is the continuity test, it's that you need to know the 3 steps of the continuity test. Also, we're going to be looking at one-sided limits today, approaching a value of x from the left or the right. You already know about this too because when we talked about the limits as x approaches c, that meant we were approaching c from the left here and we were approaching c from the right. And if these two limits were equal, then the limit as x approaches c does exist. So we've already talked about this, but we're going to see it all here. Okay, so let's look in the blue. So we know that we must evaluate f of c and the limit as x approaches c of the function separately. We have found, though, that if you can draw a function continuously, that the limit equals L, in other words, it exists, and the value of the function equals L also. So now would be a great time to look at continuity more closely. Notice I'll put C's with circles around them from now on for my continuity words there. More closely, and we'll give it a detailed definition. So the first thing we need to talk about is one-sided limits. That is, as x approaches c, left would be x approaches c, and we have an exponent of a negative on the right. Of course, we wouldn't put it in front of the c because then it looks like a negative value. This is from the left. And right is as x approaches c from the right with a little plus sign in that exponent position. So let's talk about the definition of continuity here and what the continuity test is. I will ask you when we're in class together, what is the first part of the continuity test? What is the second? What is the third? We will do that often all the way through calculus. So what is continuity exactly except for being able to draw a function continuously? A function has continuity at one point, at a point on the function if f of c, if that point passes this continuity test in this order. So all 3 of these conditions must be met for a function to be continuous at that point. If these 3 conditions are not met, then we say that the function is discontinuous at that point. So let's start with number 1. First of all, f of c, the value of the function, has to exist. That's super easy, right? We've done that all the way through algebra. We put a value of x into the function. Can we get a y out? So number 1, easy thing, we check to see if at that point, if the value of the function actually exists. The next thing we check is we check to see if the limit as x approaches c actually exists, and we call that an L. That means that we have to check the limit as x approaches c from the left, from the right, and if they are the same, then we can say that the limit as x approaches c exists. Third, number 1 has to equal number 2. The limit, the function has to approach this value from the left and right of C, and it has to hit it. So number one, does the point actually exist? Number two, does the limit exist as you approach that point? Number three, are 1 and 2 the same? So let's take a look in your book on page 70, some conditions where the continuity test fails. Take a look at this first graph here. If you notice, let's do the continuity test. They are asking if this function is continuous at f of c. You can see there's an open circle, fails the first part of the test. The point does not exist. I don't need to go any further. This function is not continuous at c. Let's go to the second graph. Let's take a look. Number one on the continuity test at c, does the value of the function exist? Yes, it does. There it is. Number two, does the limit exist as you approach c from the left and from the right? No, it does not. They are obviously approaching different y values from the left and the right. The second part of the continuity test fails, and the function is not continuous at c. Let's go to the last graph. Number one, does the value of the function exist at c? Yes, it does, right there. Number two, does the limit exist as you approach c from the left and the right? Yes, it does. Number three, is the limit and the value of the function the same at c? No, it is not. The function is discontinuous at c because it does not pass the third part of the continuity test. Let's go over to 3a. This is where it gets a little particular in green here. So, now that we can say if a function is continuous or not at a point, now we can talk about an interval. So, f of x is continuous on an open interval, coming on this side, such as this, an open interval. In fact, for now, we'll make it open. Here we go, open interval, AB, if it is continuous at every point on AB. So did every point pass the continuity test? Next, f of x is continuous on a closed interval, AB, if it is continuous at every point on the open interval of AB, and the limit as x approaches a from the right equals f of a, and the limit as x approaches b from the left equals f of b. And that would make this function continuous at every point on the closed interval. Now, this in between this here and here seems awfully picky, okay? But when we talk about continuity, we said that the limit as x approaches a value from the left and the right has to exist. Let's look back down here. We said for a limit to exist that you are approaching the same function value from the left and from the right. And we need that for number two on the continuity test. But come on over here. On a closed interval, when you try to approach an x of a from the left, you cannot. There's no function there. We can only approach it from the right. Hence, they're being very picky right here. Same with b. Notice when you're checking the limit for continuity, you cannot approach b from the right because it's a closed interval. So if the limit exists as you approach from the left, then we say it's continuous. They kind of had to be picky here to meet the definition of a limit, but at the same time, this is obviously a function on a continuous interval. You obviously can draw this picture continuously, but to bring the limits in, they had to be very picky about how they set it. 4a, functions that are continuous on the domain from negative infinity to infinity. That would be sine, right? Sine looks like this, right? Cosine. Cosine also looks like this, from negative infinity to infinity. Polynomials, lines, quadratics, cubics. Piecewise functions that pass the continuity test, right? For piecewise functions, there's obviously a room for the function to be discontinuous because it's in pieces, but if those pieces connect, then the piecewise function will pass the continuity test. B, functions that are continuous on their domains. So not from negative infinity to infinity, but on their domains. So radical expressions like the square root of x, right? Its domain is x greater than or equal to 0, right? No negative values. But from there, where x is greater than or equal to 0, obviously then the function is continuous. Rational functions, all other trig besides sine and cosine. Piecewise functions that pass the continuity test. So C, any operations using this continuous functions, such as adding, subtracting, multiplying, composition of functions, division of functions where the denominator is not 0, and powers. So again, we had a list here on 4 of what functions are continuous everywhere, what functions are continuous on their domain, and also any operations involving those functions will also make continuous functions. So what I'm going to do today is I'm going to have a second video of examples from 1.4a. These are the problems that we're going to be doing. So after you watch this video, be sure and look for the second video with the 1.4a examples.